All right, so today we are going to design a bare board, STM board, the onboard computer. Um, just the basic structure of it, enough to run, to just boot and run, and power supply. We are not going to put any sensor interface. We are going to do that in the next video. So I have a EZDA open here. So I'm just gonna maximize that a little bit. And we said the first thing, obviously, we want to do, rather what I would like to do is put the title of my schematic page here. So I can put it as a CPU section, then just rotate it a little bit and put it there. Maybe increase the size. Let's put it as 6. Yeah, CPU section at 6. All right. So this is EZDA. We can minimize this a little bit and then let's do Shift F. We said we are using STM32 F401 CCU6. Enter. So we have this board here. Place that right there. The power right there. Escape. So there are a few basic areas that we need to design this board around. Rather, we need to add a schematics to this board, and I'll just list them here a little bit quick so that we can know what to do, or we can follow the checklist. So we have the clock. So I'll just copy paste them right there. We have the power supply. We have the debug stroke programming. Debug stroke programming. We have the boot. We have the reset. And personally, I'd like to include what I call user interface. User interface. So basically, these are just two LEDs and a button to test that we are able to program and control the GPIOs. So buttons here. Just that. The first thing I'll start with is the power supply. So EZDR separated it into two sub blocks, but it is basically just one chip. So VDD is for power supply. VDDA is for supplying the analog side of the chip. VSS is the ground. VSSA is the analog ground. So if you have an analog region on your board, you can separate the ground for analog and for digital. But for this board, we will just use a very basic approach. So the first thing I want to do is have power supply here. So I add the VCC of VCC label right there. VCC label. This can be 3.3. Should be 3.3. STM supports labels. I mean, it supports voltage between 2.7 and 3.6 volts. So let me label this 3v3. 3v3. All right. So from the data sheet, it says that VBAT, VDD, any power pin or every power pin should have a decoupling capacitor. So I'll use 100 nanofarad capacitors for each of these pins. So Shift F, then we search for C, 005, 100, and F capacitor. We look for ones that are in stock. Let's look for something else. Maybe 0603. Okay, those ones are also not in stock. So, all right, I have a better method. You can use the browser for that purpose. So you can search here, open the CSC. And you search for 0603 100 NF capacitor. So you search for that, you see we have this. What about for 0805? It's a bit larger. I want to do hard soldering on this board, so the larger the resist, I mean the larger the component, the better, the easier the soldering will be. So I'll copy this part here, go back to EZDA, paste, enter, and yeah, so we have this part. Let's rotate it a little bit. I'll go back here and check that it is actually 100 NF. Yeah, it's 100 NF 005, which is okay. So I'll copy that, copy, paste, paste. This is 1, 2, 3, 4. This is ground. I mean this is also supply. So this is 1, 2, 3, 4, 5. 5 of them. Sorry, 5 of them. Put another one here. Okay. So place your ground. Place it right there. Then Alt W gives you the wire tool. So just connect those ones, the ground, and these ones together. Right, 3v3 is right there. I just move these a little bit there. Now, these are decoupling capacitors, but you also need bulk capacitors for instances when the STM32 is like, has current bursts, and we need to provide very short spikes of current. So we need a bulking capacitor, a bulk capacitor that is 10 microfarads is okay. It's typically fine. So again, we look for 005, 10 microfarads. So we have this, the price per unit. Okay, okay. So copy the number here. Go to EZDA, Shift F, Control V, enter. Place. We have that right about there. Okay. So I just move this a little bit there, copy this 3v3, paste it right here, then connect it to these guys. Connect it here. So ideally, when you're using analog voltages, you want to filter it's recommended that you filter the analog voltage using a ferrite bead or any filtering mechanism because it's analog ideally. So we will do that later on another video, but what I can do here right now today is leave a to do. I can say filter EDDA correctly. We have green here, place. So what is that? Yeah. So we'll work on that later. Okay, so we have v3 supply. The next thing we do is ground, obviously. So ground these pins. So ground that, and ground that, ground that, and ground that, all of them. Okay. So I think that is okay. That is handled correctly. Next is clock. Before I do clock, let's do debug and programming. So debug and programming. Basically, we are going to use SWD or serial wire debug for programming this board. So for SWD, we have serial wire clock and serial wire data input output. So what we do for that, we'll open a STM32 cube IDE. So I've already opened my chip configuration tool here. Okay. So here we go. Okay, so we go to connectivity, not system, uh, system sys. Then here you select serial wire, and then now you see these two pins should be enabled: system clock and system input output. So this is PA13, this is PA14. So you go back to ECDA, PA13. I'll just use net labels, those PA13 and PA14. PA14. PA14 is clock. So I'll label that net is SW clock. This is SW. Let me call it SWD IO. SWD clock. Save that, which is okay. And then the next thing I do is route these two, rather connect these two pins to a programming header, basically a header pin. So I'll use a common library for that. I'll look for header here, HDR, mail is okay. This is 3 pin, so I need 4 pin. So I'll just have ground, PCC, and these 2 pins here. So input, output, clock. Then I'll have VCC here, then ground it like that. Okay. Okay, so we are going to design the clock at this point. So we have a crystal here, as I have already searched for in the LSCSC 16 megahertz crystal. I've chosen this one. So I'm gonna place that, then connect pin 4 and 2 to ground. So pin 4 and pin 2 to ground, then pin 1 goes to crystal in, pin 3 goes to crystal out. So this is ground here. Next, I'm going to calculate the load capacitances that are required by the crystal, because application note for STM32 has this requirement that we have to have two capacitors to ground load capacitors. So how you calculate that? There's a simple formula for that, which is the load capacitance of the crystal, which is given on the datasheet, minus the typical stray capacitance, which is around 5, and then multiply that value by 2. So what happens is, if we look at the 16 megahertz crystal we have chosen, we have 8 picofarad inherent load capacitance of the crystal. So you're going to take that, so that will be 8 minus, typically stray capacitance, you can take it as 5 times 2, that will give you 6. No, it will give you 6 pf, 6 picofarads. So we look for two capacitors that are 6 picofarads. All right, so go to LC, look for 6 picofarad. First of all, I want it to be 0.8 capacitor. Let's look for that. So you can take this 6 they in stock, which is okay. So take that, bring it here, and place it. So you place those two to ground. So we can put them here, right there, and somewhere here. Then we move this a little bit. Move it somewhere. Okay, let it stay there. Then move this inside. Connect. And connect. Ground can be shared. All right. So there's another thing which is called the feed resistor, but the feed resistor here, but we can survive without that for now. Though we can put a 10k resistor at that point, but it's not it's not very critical. It's an external resistor to limit the inverter output current from the crystal, but yeah, maybe later we can improve the design. The next thing that I want to do is label these nets here just for routing purposes. This is a HSC OSC in. This is HSE oscillator out. Right, save that, and there we go. You have our crystal and clock. Now this is sorted. Then next we go to the boot pins. So boot pin basically tells us where the program, or when the chip boots, where will the code that will be running from come from. So by default boot is low, is low, which means the code that will run will be the one that is stored in memory. But if we pull boot high, then we can program the chip. So what you want to do is have a way of controlling this boot 0 pin, so that we can either control or run the code that is stored. So if you have seen STM32 blue pill, you see the toggle pins that are used to jump between programming mode and run mode. So I'll use the same mechanism here, which means I'll have to put a header pin, specifically a 3-pin toggle. So HDR, search for the local library here. I don't need something fancy, so I can use that. I connect this pin here. Connect that, then I should put it to ground first of all here, and then I have a way of pulling it high to 3v3. 3v3 is right somewhere here. 3v3 is here. So Okay, so again, label the pin. So, right, and this is bit 0. Okay, then reset pin is used for resetting the program. So I want to put a toggle switch here, which means I need to look for a tactile switch. So you can call them tactile push, tactile switches. Tactile button. For example, let's say tactiles. Yeah, these ones. Tactile button SMT search. Okay, so I want something that is let me refresh the page. Okay, so something very simple, something like let me pick this one right here. So because we are designing a satellite, the size of these buttons, the size of very small details matters for weight and for weight issues specifically. So these ones are too big. Let's see. I can pick this one, but this one is okay. Horizontal attachment style. Yeah, let me pick this guy here. Unit price. Okay, not bad. So pick that. 12 volts, 5.2 millimeters. All right. Go to ZDA. Shift F. Paste that number. Enter. And place that. So can place it right there. So what you want to do is when you press this button, it pulls a reset pin to ground. So this reset pin is active low because you can see it's negative. It's N. N stands for like the negative side, active low. So by default it's pulled high. So I want to pull it high to 3V3. So what I'll do, I'll have a 10K resistor. 10K resistor to pull that pin high. So zeros, let me see, 0805, 10K resistor. Yep, I can use this. So Shift F, paste, place. So I'm gonna place it somewhere around. Nope, let me place it somewhere around here. So it's pulled high. And then connect that. When you press this button, should go to ground. Should go to ground. So let me rearrange this thing first. It looks very ugly first of all. Let me rearrange that a little bit. So what I can do is I can put this guy here. I can put this here. Put 3v3. Somewhere around here. Connect those two. So it's pulled high. Remove this. Let's see how we can put this. Okay, so we want to put it to ground. So I'll just label this button as reset. So typically what you want to do is clean this part here from high frequencies or decouple it from high frequencies using a capacitor. So I'll just copy 100 nanofarads, paste it and put it somewhere around here. Specifically a way of debouncing this thing, debouncing the reset circuit in hardware. And yeah, I think we are good. So when you press this, it goes low, resets the chip, which is okay. So the problem here is I need to be able to, I need some space here. So I'll just move those guys, just rearrange a little bit, reset. Okay, put 0, can put this guy here. Then I also label this net as NRST. Okay, so VCAP is a pin that STM says it requires a capacitor. Let's look at the datasheet. So if we look at functional power supply schemes, we're looking for VCAP. Okay, yeah, let's see. VCAP. Yeah, so depending on the package, 1 or 2 external ceramic capacitors will be connected on the VCAP 1 and VCAP 2. Okay, so let's have a resistor here. I put this here and then paste, copy that, put it there, put the ground somewhere there. Okay, so reset. I think this part is handled. Wake up, we don't need that. We can wake up from the RTC. Okay, so at this point here, I don't need these guys here. I can just connect directly and then rearrange, just put it close to this point or somewhere there. Okay, so we have handled power, clock, boot, reset, user interface. So what we need for the user interface is I need 2 LEDs and 1 button. So I'll go to LCSC again, look for LED green, SMD. So we have this, what's the size of this? 2835 is too large. Let's look for C. It's a small 0805. LEDs come with different packaging, but no, we can get 005, which is it's in stock. Which one is in stock? This one is much more available. What's the color? Let's see. They are not indicating the color of this thing. All right, close that. Let's look for this It's not even available in the picture. This is yellow, so you can use yellow. There's green here, and it's in stock. So yep. So copy the part number. Go to ZDA Shift F, Control V, and place that. So we place that somewhere around here. Let's place it in this side. So you can have a 200 ohm resistor here, 200 C005 resistor, 200. I mean, you can calculate the resistance you need, but 200 is fine. Let me place this one. Yeah, this is more expensive, 0.2 per unit. This is cheaper, and it's in stock. So let me use this. It's cheap. It's cheaper than the other one. Control V, enter, place it right there. Then you ground that. Now we need to know which, or rather, we need to know where this LED is connected to. I'll just rename this to green. I'll call it user green. Okay. Next thing we need is a tactile switch, just to be sure that we can take register inputs. When you are testing the code, rather the board. So ground that, and this part is not connected, and this part is not connected. So redo. You should have a connection between this point and that point. So what you want to do here is add a debouncing capacitor at this point. So you can just copy this, the one that is already available. So let me place this one here and rename it to user PTN, user button. Okay. So I'll just move these guys somewhere around here. Rearrange that a little bit like that. And this one like that. So Control V. Okay. Then we can do that. Now, what we need to do is configure the STM32 chip for these two pins. So this is LED. So I'll label this and call it user button, and then I'll call this user LED. Save. So we go to our cube IDE, configure those two pins. Okay, it's taking time to wake up. So these pins are subject to change because we have not added the sensor interfaces. But for now, we can, have them as placeholders. Just show you how I'm going to, or rather how I'm planning the architecture of this thing. PA9 and PA8. You can start the other way around, like you can start from this side and go to the STM. You can start whichever way you want. So I've used P9, which is probably you at, yes, you at 1. So probably that's going to be used by something. Let me see. PB7. Oops. PB7. Or you can use just more than, you can like use P9 and P10 for UART or PB7. So let me just use them the way they are. So what I've connected on P9 is a user button. So P9 GPU input. GPU input and label user button TN. And then P8 is user LED. So P8 here, LED is output. So user label is user LED. Okay, so save that. Okay. So it's user LED. User LED green. Just to be, remain consistent with the naming. You should name them how you named them in the code. Okay, so I think that part is handled. User interface reset is handled. Boot pin is handled. Clock is okay. Bug is okay. Power is alright. So okay, so the next thing is just to rename this guy here. This is the onboard computer. Onboard computer. So what I'm gonna do is just arrange the schematic to look neater. Let me make this 8. And I have this as the power. Somewhere right there. Clock. So I'll label this as clock. Let me delete that. 5. No. Big 5 4. Okay, so that's clock. Let me make it green. I mean black. Let's just see. And here we can have a bag. Okay. Let me put it here, the bag. And here we have our boot toggle. Then here we have reset. So this button is not connected. These pins are not connected. You can put the no connection label there for DRC. Then we have power here. So we have power. Okay. I think that should be in order. Then this is user buttons. Let's use them. user interface user, yeah, just user. I like it better in the small letters, so put toggle. Okay, all right, so I think this is in order. Next thing we are going to add is what we call sensor interface, but that will do it in the next time. So right now this board is okay to be powered and can run. Basically, you can upload code and toggle these other readings from this button and toggle the user LED, which is in order. So next time we're going to add the functionality for the sensor interface, but for that we need to design the sensor board first and know what sensors we are interfacing before we add them here or commit to our changes. But either way works because you can make changes here and on the sensor board simultaneously. So that is okay, and yeah, I'll see you next time.